Hello my friends, welcome again to my video channel. Today we'll start a new project, AEG receiver E800. The brand AEG is maybe better known under the former brand Telefunken, which was a German company in the, I think it got out of the market in the 80s or 90s, don't know exactly. The brand existed, or I think it still exists today, but not for such receivers because they are not built any longer. This is a receiver from the late 80s, early 90s. It was built, I think, in the 90s. Also, the documentation is from 93, I found here. It's a shortwave receiver from 10 kilohertz to 30 megahertz, and as we see, it's a commercial unit. It's not an amateur radio receiver. Would have been a little bit too expensive for an amateur like me and others. It's for commercial use, military, marine, weather stations, intelligence agencies and others who have money, who get the money from the taxpayers, so the price is not so relevant. It is a little brother from the bigger unit E800, E1800. This is the E800. It's a smaller one, but has similar data. It has a lot of knobs on the front. I will switch it on later and then we will see the problem. Tuning knob, frequency display, mode, bandwidth selection, AGC switching, AF gain, antenna selector and so on. The receiver concept itself is a purely analog concept. Only the control functions are digital. It was in the late 80s, the time when the first digital components went into receiver technology, not for reception itself. It's not a software-defined radio, it's still hardware designed. Or defined, not designed. Yes, designed also. Designed and defined. It's a truly analog concept. We will see it later. I will show some parts of the manual. By the way, I have the complete manual. It's the original manual. It's important. And it was only in the control part, digital. We can see here frequency. The synthesizer is of course digital. On the rear side, there are some connections also. We can see antenna input, IF output. Here's the connection of the also AF output, impedance 600 ohm, isolated output via transformer. Here we have the output for an external antenna control unit. We can switch between several antennas. Here we have some digital outputs for, I think, radio teletyping and so on. This unit is obviously not equipped with it. It's not important. And here we have a data interface, which is also not existing. Then we could make a remote control of it. This would make sense for automatic listening for stations who scan the certain frequencies or bands. It was designed during the Cold War, before '89. So it was for the purpose also for military use. Well, that's it from the outside. Now let's talk a little bit about the concept. This is of course the most important part. It's the input. It's the HF section. We have here the antenna input. You can see it, yes. It's a low pass filter. It is not tuned during the operation. It's a fixed low pass filter. That's input circuit, and here we have a double balanced mixer with fades. The fades have no power supply. They are only fed by the oscillator, which is a power oscillator. Double balanced, that's the input. The oscillator is operating from 42.2 up to 72.2 kilohertz. The first IF is 42.2 megahertz. We have here the roofing filter. That's the output of the IF from the mixer. First roofing filter, small amplifier, which is controlled by the AGC, I think. Yes, Regspannung, that's the AGC line. This transistor here is the AGC line. This is AGC line. Not this transistor, sorry. Here we have the attenuator with pin diodes. Second roofing filter 42.2 megahertz. And here we have another amplifier, and that's the second mixer. This is a second mixer with a remixer which receives 42 megahertz, and the second IF is 200 kilohertz. So we have a conversion from 42.200 megahertz down to 200 kilohertz. The oscillator is 42 megahertz. And for better image rejection, we have two here and here, two roofing filters plus one, let's call it a trap. It's 41.8 megahertz. This is the image. When we have here 42 megahertz oscillator, 41.8 megahertz would also create 200 kilohertz. And to prevent this, we have the two roofing filters plus this frequency trap, and the crystal here is aligned with this coil for, I think, best suppression. So the output is 200 kilohertz. That's the second IF, and the IF where the demodulation is made. But we see here truly analog concept. Only the oscillator, of course, are digital controlled. This is the IF part, the selection. We have here the input. Sorry. You can see it. We have here the input. These are selectable filters. The filters are selected by these transistors. They are switched on off. And the signal is fed through these transistors. This here is the output. And the selection of these transistors is made via these digital switches 7406. And this is digitally controlled, as we can see. It is digitally controlled from the controller part. But again, the selection is purely analog. We have analog filters, no digital filtering. This is the IF section, the amplification behind the filters. We have here several stages, and the gain is controlled by the transistors in the emitter, and when the emitter resistor is bridged by this capacitor, the gain is increased or decreased by 28 dB. And these attenuation transistors are controlled via these lines, which are also digitally controlled. So we have a combination of analog amplification and digital control. The digital control part comes from this DAC, digital analog converter. DAC, I think it's digital analog converter. It is controlled here, and the output goes to via this amplification on this op amp to the HF part, and this is the control voltage for the attenuator in the input of the signal in the first mixer or the first roofing filter, as we have seen. Here we have the demodulator part. The RF signal is fed in here. This is MC1596. This is an SSB demodulator. It gets here a second signal, 200 kilohertz, plus minus. I think this is the BFO. And this is the IF signal, and this is the output. And via this diode, selected by this controller here, it's fed to the AF transistor. And then it's to the NF output, AF output. And we have the speaker. Here's the speaker. Should be a jumper there. Then this is the output. We have this jumper to TDA 2003, and we have the loudspeaker. The FM demodulation is made separately, and the input, as I have seen from the NF signal from the FM demodulator, is F3 frequency modulation, this input, and this diode is switched via this controller. And the AM signal, as I understand, AM demodulation is made here in this op amp with the diode, and it goes there, and it is this one, A3, this AM signal controlled via this controller, this AM signal. And as I understand, we have here the generation of the AGC voltage. There is a switch between, should be fast and low also, depending upon the mode. And as I understand, here we have the AGC output. I have to check it whether it's true. Sometimes it's useful to read the full description. The manual is very complex. Yes, indeed, this is the AGC circuit here, of course. And here we have an analog switch, and the output of the AGC goes to this output pin and is fed to the central control unit, where we have a digital control of the AGC voltage, as we have seen in the IF part, where we have some switches in the emitter path of the IF amplifiers. Here we have an additional demodulator B8E. Here and here is connected to the signal path here. This B8E is a AM modulation with 2 independent sidebands. As I think if this option is installed here, I will see it later when I try to operate it, but it's a special AM signal. It's like SSB, USB and LSB on the same frequency, but with a carrier, so it's an AM signal with 2 independent sidebands. We also have some different FM demodulations for teletyping, telefax and so on. It's a commercial receiver from those days with special modes. It's also included here. This is the first oscillator, which runs 42.2 megahertz above the reception frequency. So it runs from 42.2 up to 72.2. This is 10 kilohertz to 30 megahertz reception. This is the oscillator. The ranges are switched by these transistors, controlled from the central control unit. This is the oscillator part, U310. It's a standard oscillator, buffer output. And here we have the control voltage for the VCOs. The steps are generated digitally by this DA converter with various with pull-down resistors. And here we have the DA conversion with the steps. This is a tuning by steps, and the fine tuning is made by this sample and hold part. It's a sample and hold circuit which does the fine tuning. This is part of the analog PLL circuit. It's a rather complicated circuit. I admit I don't understand it in the moment in detail. We will see whether we have a problem in here. Then I will focus on this topic. This is part 2, digital part. You also see it's a lot of circuits. Not necessary to discuss it in the moment in detail. And this is part 3. And this is also the second oscillator, as I see. Yes, it's a 42 megahertz oscillator. Well, that's the oscillator part. Here we have the page 4, that's a BFO 200 kilohertz output. It's derived from a 2 megahertz signal. That is the location of the components. Here we have the front panel with all the switches. connection to the data part of the central processor unit. The next part, page 2. Also a lot of switches and indications. Wow, wow, wow. That is a front panel, a loudspeaker, LED displays. It's a very, very good documentation. And this is a central control unit. Zentrale Steuerung, central control. Oh yes! Hope the problem is not there. Aha. Of course, a page 2. It would be too simple when it is only with one page. We have 2 pages. Also the layout. There's a demodulator part. F1 and F4 frequency demodulation. Okay. Also not so important in the moment. I look for the power supply. There's the output for the, I think for the RTGY. It's 40 milliamp output, yes, as I remember, it's for RTGY machines. The tone output. And this is a power supply. And surprise, surprise, what do we have? We have, you see it? We have a truly analog power supply, not a switched mode. It's an analog power supply. Power transformer, rectifiers, voltage regulators, plus minus plus 5 volt, plus 12, minus 12. Standard, as we know, in those days the engineers decided to use a linear power supply. It's good for a shortwave receiver not to have a switched mode power supply in it. We know why. There is one specialty. There's a relay. This switches the inputs of nearly all voltage regulators or the outputs. And this is a so-called standby. In standby mode, when the receiver is switched off, we have a continuous connection to the power transformer. There is no switch. And we have one output which is constantly fed with 5 volt. And I think this supplies a standby circuit, so we can switch on and off the receiver by standby. And this transistor controls, sorry, this is standby. This is low standby, this is standby. And with this transistor we can activate the relay, and then we can switch on the whole receiver because all power supplies are switched on. Maybe we have a problem here because the owner told me that the receiver does not switch on completely. There is some strange behavior. Okay, that was a tough ride through the schematic and through the concept. I find it's a very interesting concept, especially the direct conversion from 42 megahertz down to 200 kilohertz without another IF between. So we have only 2 IFs. The first is the roofing filter, 42 megahertz, and the second one is 200 kilohertz, where the selection is made with switchable analog filters. But now let's focus on the problem. The receiver is connected to the mains, to the power. The only indication which is lit is standby. As we have seen, standby is energized. Everything is switched off. When I switch on, it works. Crazy, crazy. No, it works not. Now it works. What shall I say? Obviously there's a reaction, there's life in it. I will take off the mains. The sound is a little bit strange. There's a speaker inside for indication of problems. Maybe if this is a speaker, the beeper, not this one. I think there's another beeper inside. It reacts. I don't know whether it's receiving. This seems to be a birdie, 13 megahertz. I hope I can reproduce the problem. I will try it again. A possible problem could be the battery. Here we have a battery inside. It's on the control board. Here we have it. Lithium battery. I measure the voltage and see whether it has 3.5 volt. That's the nominal voltage. We connect the multimeter. I'm measuring 3.258, 3.26 volt. 3.55 should be the nominal voltage. There's some loss in the voltage, but the lower value, lower limit is 2.5 volts, so we are above this value and there is no problem with the battery. Next check is the power supply. We have here the power supply. These electrolytics look good, they are not bulged. The case is still sealed. What we see here, it's this shiny stuff here. It's not a leakage, it's a glue. It's a black glue. We can see also here, everywhere. Even the rectifier. This rectifier is glued to the board. And we can see the same glue on the other boards. For example, we can see it here. Here. This electrolytic is also glued. It's a black, looks like acrylic glue or similar, or plastic, don't know exactly, but it is not a leakage. That's important. We have also no problems in the power supply with the fuses. They are not corroded, so there are no problems. Could theoretically be that we have inside the fuse a contact problem. Could be. One of the suspects is also this relay. We have seen there's a relay for the standby circuit, and when there's a contact inside which is a little bit dirty, and when it is activated, sometimes switching on off, suddenly it will work again. It will clean itself by the voltage. This could be theoretically the cause of the problem, which is in the moment not existing because the relay was activated in the last days several times. Maybe it was a self-healing. I don't believe in self-healing, but in this case it could be that the contact is cleaned. Yes, could be. I will talk to the owner, ask him what he proposes to do. I will rest the receiver here in my basement and wait sometimes or 1 or 2 weeks and see what happens. I found in the manual an option test. This receiver has an option to do an internal test of all functions, what is possible. So it is necessary to press second function, test, and then 0, 0, exe. Do we see? Okay, no error found. A short check. I use my signal generator. 29950 is a signal. Minus 90 dBm. Let's go down to minus 100 dBm. It is followed by the S meter here. When I go to LSB mode, a little bit funny, this tuning aid. Maybe it is more or less thought for FM reception with frequency shift keying or so. May be helpful, but for SSB, in my opinion, it makes no sense. I go down in the level minus 120. This is 0.3 microvolt. I go up in the level minus 70. Okay. 60. This is 0 dBm. Okay. It's also indicated. Okay. The receiver doesn't like this strong signal. But this is 300 millivolt. Ooh, okay. Go down to 100 microvolts. Let's use FM. Okay, you see here two frequencies. It works. Let's go to AM. Where is it? It's an AM signal. Also okay. Well, I really can't say that there's a problem. Don't see any problem. Frequency input can also be done with the keys in kilohertz. For example, 10 megahertz, 10000. Enter is 10 megahertz. Well, as I said, I have to talk to the owner. I talked to the owner what to do, and we decided to do nothing. To swap the relay and the power supply board could be an option, but I think it's not necessary in the moment. And I switched it on after a week. It came up, it fired up, no problem. So we have time to do something else. to play around with this receiver and to see what we can receive. I've connected a small external antenna. It's a mini whip antenna, an active antenna on my terrace. My big antenna on my roof of the house is not active in the moment. I have to reinstall it. So I only have a small antenna for shortwave reception on my roof. And this active antenna is good from frequencies, I think, above 50 kilohertz or so. And I'm here on 43. There's nothing. The range 10 kilohertz. What we hear is only urban noise. Monitors, computers, whatever it is. Here's the time standard on 60 kilohertz. I have to admit I don't know what it is. I have to look into the frequency lists, but I'm too lazy to do this. The next station we can receive is on 77 kilohertz. It's a time standard and a frequency standard. It's transmitting time for clocks and also date. And it's a frequency standard on 77.5 kilohertz. It's the DCF 77, Delta Charlie Foxtrot 77 station. It's in Germany, and it can be received all over Europe. Each second a signal, and each full minute, you heard it, 1 second is missing, so that's a full minute, and other informations are also coded in the signal. Nothing else. This is another telecontrol station. It's for remote operation of any industrial plants and so on. It's a European station also. Similar station. Another one. This could be a radio station now. Yes, it's an AM broadcast station. This tuning aid is a lot of it's a sort of frequency spectrum, and the red one is the center frequency, and when it is in line, it's the width. I can change it. Okay. And here we will receive some NDBs, non-directional beacons. It's for aircrafts. Mike India Quebec. Now we're on the broadcast range. The bandwidth can be selected up to 10 kilohertz. Not so many stations, many broadcast stations have been shut down in the last decade, AM broadcast stations, so it is rather quiet on the frequency. Ugly fading. This is the end of the AM broadcast band. Now let's go to some shortwave bands. For example, 40 and 41 meters amateur radio bands. In SSB mode, the bandwidth can only set between +3, that's upper sideband, and -3, that's lower sideband. 3 kHz bandwidth. The bandwidth cannot be changed here in the SSB mode. That's a little bit disadvantage. Let's go to 7000 kHz. We are in LSB mode. Not so much reception. It's evening. Chinese station here in Europe. Let's go down to 6000. Again, Chinese station. Let's go to 20 meter band. It's evening, it's the wrong daytime. I've forgotten the 80 meter band. 3500. the quality of the speaker is extremely bad. It's a cheap speaker, but a better speaker cannot be connected to the receiver. There is no connection on the rear side for a better speaker, only for the headphone. Some amateur radio stations. But rather weak. Well, it's not the right daytime for it. The antenna isn't the best. Let's go to 10 meter band. 28,205. There is a beacon. Oh. 6 dB. It reduces its power. I can go to CW reception. With reduced bandwidth, 300 Hz, 600. This station is approximately It's approximately 70 kilometers away from me. It has 50 watt and now reduces the power in some steps. Okay, that's a short impression of this receiver. It has some other options for FM reception, for RTTY, and for facsimile reception, with inverse as output on the rear side for external decoders and so. We only have SSB here. The B8E is not equipped. This would be AM with 2 independent sidebands. This option is not installed. Makes no sense. We have here amplitude and frequency modulation with variable bandwidth in both modes. CW we can... okay, data out is also not equipped. It's a nice receiver, but for true amateur radio work I think it's not the best choice. It has no notch filter, no noise blanker. The no passband tuning or passband shift, and the bandwidth in mode SSB is standard. It's 3 kHz. A little bit too wide for SSB reception. Better would be 2.4 and a little bit less. So this receiver is a commercial receiver for maybe RTTY in those days, teletyping, data transmission reception, also with some cryptological machines for embassies, commercial applications, military, and so on. For amateur radio, I would use a different one. There's a big brother, the E1800. It's the smaller one, the E800. The E1800 has more options. There's a bandwidth control in it, and I think also notch filter and such things. would be better for this purpose. This one is a cheap version. It's a Volkswagen people's car, but it was also not cheap in those days. Okay, it was nice to have hands on it, to do some investigations, to play around a little bit with it. We had no project here, no real project, but I made some video sequences about it, and I think it would be too pity to throw it away, to delete it, so I will show it, or I show it to you. And now that's the end of this project, which wasn't a project. We only had a small demonstration of such a receiver. Again, when you will use it for amateur radio applications, you shouldn't forget what these receivers have been designed for. Not for amateur radio. They have been designed for commercial applications and for operators on any in any environment which is not a technical one, in embassies, in big companies which have foreign offices in foreign countries, which need some communication with the headquarters. And those guys are not for sitting there for hours listening on the bands. They are switching on this receiver like a telephone, want to have a connection to the other station, exchange some data, and then switch it off again. So these transceivers have a little bit different performance and market design, not especially designed for radio amateurs. Well, that's it. When you buy such a receiver, you should know what you buy. And do not expect miracles. For amateur radio operations, there are better receivers on the market, even in those days. Stay healthy, stay tuned. See you on this channel.